by different stakeholders in decision making, and we continue this cycle of development. Our group has three professors. It's chaired by Yannis Athanasiades, and our research lines go from knowledge representation to learning representations to understand complex phenomena. We also do we do research on how we can integrate and develop methods that pay attention to domain knowledge. So we have onboarding and developing also methods related to scientific machine learning and also complex data representation across space and time. We have also two recently appointed assistant professors with expertise in scientific machine learning and also Earth observation. So please stay tuned to our contact and progress concerning those areas as well. So what I'd like to talk is about how we can move from data to knowledge, and especially paying attention to explainability and responsible use of technologies. And one thing that I would like to bring here to the table is this, the original vision that I mentioned before also apply for health and medical data. So how we can sense, put together complex data, heterogeneous data from different data types in such a way that we can support, better informed decision making. I would like to bring to the table today three different perspectives. The first one is how to encode knowledge and how we can perform science-informed decision making, how we can leverage predictive modeling to a different level in the sense of reproducibility and also reuse of models, and finally talk a little bit about our initiatives concerning responsible AI, ethical, legal, and societal aspects. So let's talk a little bit what we have been done recently related to knowledge representation. So we have some research activities connected with the creation of knowledge graphs out of, I'd say, biomedical scientific literature, for example. And the idea is to explore this kind of knowledge graph in science-informed decision-making process. So we have been investigating NLP and more recently, I would say, advanced LLM-based methods to support the identification and the encoding of relevant knowledge in specific domains. I can give you an example from a recent research dedicated to the use of LLMs subject to the definition of different prompt strategies and also subject to the definition of well-defined domain-specific ontologies. We use these kind of methodologies for the creation of knowledge graphs. I'll go back to this example later on. Concerning predictive modeling, maybe some of you or most of you in the audience have been exploring multiple methods ranging from regression to advanced segmentation and detection approaches. Here in Wageningen and also before joining Wageningen, I have been also conducted some research related to typical machine learning problems. Involving, for example, regression problems to predict specific forces while patients are walking, so that we can leverage new opportunities for sensing using computer vision, how we can perform time series classification based on sensed data, and how we can leverage diagnosis performance using this. We have been playing also with different multimedia data, ranging from problems related to tissue classification, also video classification, in this case, cardiac related videos. And And also, of course, we played a little bit also with segmentation problems, trying to identify, appropriate computer vision methods for this kind of problem. What I'd like to bring to the table here in my presentation is that all or most of those pipelines can be organized and structured in such a way that we could reuse and document those workflows in engaging in a promising way, in such a way that practitioners, including researchers, physicians, stakeholders, they could reproduce the results. They could find the appropriate components being used in these predictive modeling solutions, and try to, of course, annotate these semantically so that we can, of course, document precisely how and which data were used in the training process of those algorithms. Concerning responsible AI, we have been involved on an ELSA lab. It's an NWO-funded project related to the design of AI systems, especially for sustainable food production. The application that we have been considering is related to recommendation of treatments, even though the target application is concerning treatment recommendation in the context of animal welfare. We do believe that our solutions can be extended easily to, of course, more general solutions. So what we have in mind, we have been developing a kind of AI-based methods for the construction of knowledge graphs. Knowledge graphs not only pay attention to the treatment characterization and also the individual characterization, but also to ethical, legal, and social aspects. For example, we could encode using knowledge graphs what are I would say, the ethical, inappropriate side effects of specific drugs, and encode this and take into account this in the process of recommending a treatment. And more than that, we have been exploring, for example, when you rank a list of possible treatments, how we can leverage large language models to provide suitable explanations about possible ELSA aspects, ELSA issues connected with recommended items. So this is one research line. To close my presentation, I would like to mention some aspects about what would like, eventually to consider for future collaborations. I would like to continue my investigation on changes over time, especially in the context of encoding knowledge evolution in the specific areas, of course, exploring knowledge graphs eventually. I would like also to find ways to move forward with the possibility of encoding the scientific discovery process, not only in digital labs, but also in wet labs, using also knowledge graph representation. Here, there is an inspiring paper that maybe some of you may have read before, and this is a kind of direction that I believe could play a role. And another direction that our group is pretty much interested is in the development of foundation models for multimodal data and agentic systems that can be explored in guiding stakeholders in the health and medical domain in their decision-making process. So the take-home message here is how we can support science-informed decision-making, and our, I would say, building block here is to explore knowledge graphs for that, how we can move forward with reproducible, explainable, AI-driven knowledge discovery pipelines. And our claim here is to move forward with shared data and AI infrastructures to support predictive modeling, and the development of ELSA-compliant AI systems, paying attention to predictive modeling methods, paying attention to existing infrastructures for knowledge management. So I'd like to thank you all again for the opportunity, and if possible, I would love to take some questions.
Thank you very much for your presentation, Ricardo. So maybe we can move to the second speaker first, and there will be like 5-10 minutes question round at the end of this session. Our next speaker is Dr. Francisco Souza. So he's a researcher at IMAC and OnePlanet. His work focusing on sustainability, data-driven innovation, and the development of digital twins to support environmental insights and decision-making. Francisco, the floor is yours.
Hello, good afternoon. Thank you for the invitation for this talk. I'm just seeing, let me just share my slides and then we can start the presentation. Yeah, so I'm Francisco Souza. I'm a researcher at IMAC / OnePlanet. And today I will talk about a bit about OnePlanet and how we use cheap and digital technologies, AI, to help to solve the biggest challenge in agriculture, food, and health. Yeah, so OnePlanet, for those that don't know, was established 5 years ago with the mission to create technologies or solutions to tackle the global challenge in the area of agriculture, food, and health. When we look at the global challenge, you can see here, as it's clear that we need to act. And specifically with the increase of the population, there is increased need of for health, food, and nutrition to contribute to prevention of disease. And here at OnePlanet, we work with industrial partners to accelerate innovations and to create scalable applications which can have a large impact. And basically, we focus on 3 domains. That is health environment, health food, and health life. Within those 3 domains, we create new applications that we expect, right, that will result in a sustainable future. And we are absolutely convinced that the digital technologies and the AI and the nanoelectronics and chips innovations are the key to success. Yeah, so that is an overall view of OnePlanet Research Center description. So OnePlanet is an established partnership between IMAC, the Netherlands, the Radboud University, the Radboud University Medical Center, and the Varney University and Research. So we have offices at the VUR campus, Varney, where I'm based in, but also we have offices in the Radboud campus. So we do both. We do both fundamental and applied research, and we work together with companies, research institutes, schools, and citizens as well. So I think you all know about VUR, the Radboud University and the Medical Center. So let me quickly introduce what is IMAC for those that don't know. So IMAC is a world leader in nanoelectronics and digital technologies research. So it has about 4,000 researchers worldwide. I think it's now 5,000, and the headquarters is in Belgium. So we have offices in the Netherlands, Taiwan, Japan, America, China, and India, and we have more than 500 industrial partners. I think this number has grown as well. Many spin-offs, companies, and startups. And perhaps just short statement about IMAC's mission is that we focus on research and development to create real-world solutions. And I think it's here, but IMAC is a non-profit organization. Here at OnePlanet, with this consortium, we use artificial intelligence as the key enabler for many of the domains that we work with. We apply AI to extract insights from complex data, to optimize process, to personalize interventions in health, food, and environmental systems. In the next slides, I will give a high-level overview of some of our applications. So I'm not in all those areas, so please don't shoot the messenger, okay? Yeah, so let me briefly talk about our sensors and our AI solutions for health. Most of the sensors that are shown here, I will perhaps detail a bit later, we build in-house. So IMAC, together with IMAC, we also have a small team here for building sensors. We build the sensors. So the premise is that the traditional health models are often static and based on population average, making them less relevant for individuals and slow to adapt to new data. So integrating diverse real-world data streams from different sources like sensor data, clinical records, and behavior is also a major challenge. So our main goal is to create in-house non-intrusive health sensors, such as the ingestible pills. So basically, it's a pill with pH and ORP sensors embedded, wearables sensors, and smart toilet sensors. And that generates a lot of data that we combine with AI pipelines. Of course, and these enable the continuous, objective, and personalized data collection in real time and with the minimal disruption to daily life. Of course, this brings a lot of challenge in processing the data. For example, one of the problems is the unstructuredness of the data that requires manual integration for operation. So we have a team for leveraging data pipelines and machine learning operations. Also, it requires domain knowledge and expertise. So we create hybrid models, including mechanics, physics models, chemistry models, together with the data. We also create personalized models by subjects using local collected data. Typically, the models are trained only once, and here we typically train the models continuously and following the machine learning operation strategy with data then when needed. We deploy typically our work on our solutions in the cloud, so because it's easier to maintain and validate among the peers. Also, most of those models requires a lot of data, health data models, they require a lot of data. And we also have strategies for generating synthetic data to augmenting the training of the machine learning models. So this is just an overall highlight of the health applications we have here. And also we have some digital twins in health, some AI offerings. For example, the digital twin technology in health that has that includes the multimodal data integration and the unique data sets. We have also a large number of data sets from different applications. Also, we do modeling uncertainty and personalized strategy. So we like a lot to use Bayesian modeling because that we can incorporate the expert knowledge and the domain knowledge, and also to quantify the uncertainty. Also, the solution allows real-time data collection and operational pipelines. We have a standardized, scalable code base for research and health management. And also, we are very keen to find partners, mainly industrial partners, because we can facilitate the development and operationalization of AI for health systems. Let me just talk about perhaps two packages that we have. First is the Planet X, is one of the core modules that we have within the Digital Twin Engineer Suite for health applications. Its purpose is to enable the integration and operationalization of multimodal health data that combines signals from various sources, multimodal data, clinical records, and behavioral data. So the main aspects of Planet X is the ability to handle multimodal data. Also, it allows the development of advanced models that incorporate domain knowledge, uncertainty quantification, and so on. Also, the Planet X is designed for real-time data collection and processing and the creation of AI pipelines. And also, it's scalable, and also it complies with the health data regulations. Another package we have is the BioSync. It enables basically the integration, synchronization of multimodal health data in the edge. So it doesn't go to the cloud, and it supports real-time monitoring and personalized modeling for digital twin applications in health. One of examples of digital twin applications we have is the good field link. It uses ingestible pills that is equipped with the pH and ORP sensors to monitor the physiological parameters through the gastrointestinal tract. This enables detailed real-time modeling and synthetic data generation for good health research and clinical applications. And yeah, I think a recent paper was published in Nature Electronics describing this smart sensing pill, which is a nice reading to go through. Also, we have the hydration twin. That is basically, it integrates the data from a smart box, a smart snack box that was created in-house, urine sensors also created in-house, and wearable device like the Garmin watch, the smart watch, also made in-house. And these sensors, they collect data in real time. We send that to our data pipeline, and then we can monitor the hydration status, the dietary intake, and the physiological response, where you can then support personalized hydration management and simulation of interventions. And then we have the biosensing at home, that basically it employs a smart toilet that has some sensors on top of it, and urine sensors to capture the physiological and biological measurements in everyday settings. It's a very nice project, by the way. And this approach enables the non-invasive continuous health monitoring and provides high-quality data for both clinical care and researcher. And of course, if you want to know more technical details about any specific sensor or application, just let me know at the end of the presentation. Let me now jump pretty quickly to some of our precision agriculture applications. In this example here, we employ multimodal sensor data, LiDAR sensors that is built in-house, and high-speed spectral sensors also built at IMAG, and RGB cameras to generate point cloud attributes. So we generate the virtual representation of our orchard, and then we can reconstruct the objects, for example, the tree, and then we can use algorithms for decision making, for example, for pruning the tree in the best location to allow healthy growth of the tree. And I think the next slide, I have some examples what I'm talking about. So this robot here, this tree and this environment was created using those sensors, and then the robot is acting on the virtual space, but also in the physical space. So it's an example application of smart pruning. And on the left, you can see now XR application of smart pruning, where the user can train and prune the tree. We still need to include the growth models of the tree to check what is the influence of cutting a specific branch. So also we have applications for the environmental applications. We have this NitroSense box that I think is installed. We have about 200 NitroSense box installed in the Netherlands. It measures the nitrogen airborne gases. Right now it uses electrochemical sensor for measuring NO2 and ammonia. And we are moving to a track where we don't use the electrochemical sensors, but we are moving to a laser-based approach for measuring these compounds. So because these electrochemical sensors, they are very cheap to deploy. I think each of those sensors, they cost about 100 euros, so it's pretty cheap. The other types of sensors that are more high quality, they cost around, it can range from 1,000 to 50,000 euros. And then the idea is that we create, in that we generate a lot of data, and we have our data platform, because this is Silver, where we collect all the data. And then from the data, we create, for example, a sensor twin that is a digital twin of the electrochemical sensor that enable us to create adaptive calibration methods, and also to support the predictive maintenance of those sensors, because those sensors, they have a limited lifetime. I think about 1 to 2 years. It depends on the amount of sensed gas. And then the idea is to bring out for a more complete view of the problem. So we do a monitoring network. We also have strategies using Bayesian modeling for the source estimation and attribution. So know who is emitting and how much it's being the emission, and that all to support the decision making. I think that's also another application for the food side. Pretty quickly, the same principle of the environmental sensor. We have IMAC UV transmission sensor that can that collects data in the algae process. That sends the data to Senseiver, and then we can create digital twins to monitor and predict the nutrients and the biomass of the algae. And then we could do smart control and smart intervention in the algae process. Yeah, that's most of the information. Just a general high-level view of what we do here at OnePlanet. We can also visit the website. To have the Dutch and the English version. They are different. So if you are curious, you can do the both research. And also, if you have any specific question, you can email me, and I can forward for the right person to contact you. That's it. Thank you.
Yeah, thank you very much for your presentation, Francisco. So if anyone have any questions, please feel free to raise your hand. Francisco, I saw there is already a question to you on the chat. Can you respond to that?
Yeah. Let me check. Yes, indeed. I think the main difference here is about our sensors. I think Peter had the question, right? Peter asked the question. I think the main difference, from the traditional applications is indeed it's our sensors. The pipelines that we use then to prove that the application it works in a general view. We don't look to bring innovation to the data pipelines and the strategy in general, but more on the modeling side and the sensing side, because we are also applied research center, so we don't. We also want to prove that the sensors and the data together with some pipeline, it works well in practice.
Yeah, does that answers your question, Peter? If anyone else have a question, please drop it in the chat or raise your hands. Or if you see any like potential opportunities for collaboration. No one? Okay. So I think that's a quick session, and I will type the contact details of these two speakers in the chat. So if you interested in learning more about their projects or want to explore potential collaboration opportunities, feel free to reach them out directly. And we will also share their presentations later on by email to you. Yeah, so thank you very much for attending this session, and have a nice day. Bye.
Thank you. Have a nice day.